Hello everyone, I'm Timothy, a high school math and physics tutor who is actively studying graduate level mathematics. In this video, I'd like to cover the second isomorphism theorem. Without further ado, let's begin. Let G be a group and let HK be two subgroups. Assume that H is contained in the normalizer of K, where the normalizer of K is a set Nk with all elements X in G such that Xk X inverse equals K. Then H intersects K is obviously a normal subgroup of H. Since H intersects K can be trivially verified as a group, let's focus on the normality. Let X be the element of H intersects K. Since X is in H, for all H in H, Hx H inverse is in H. Meanwhile, since X is also in K and H is contained in Nk, Hx H inverse is in K. Thus, Hx H inverse is in H intersects K, and H intersects K is a normal subgroup of H. And equally obviously, Hk equals Kh is a subgroup of G. Again, since H is in Nk, for all H in H and K in K, Hk H inverse is in K. In other words, there exists K prime equals Hk H inverse in K, which implies Hk equals K prime H, hence Hk equals Kh. And once we have the set Hk equals Kh, we then can get all of the corresponding inverse elements in it, which allows us to verify that it's indeed a subgroup of G. There is a surjective homomorphism from H to Hk mod K, associating with each X in H the coset Xk of K in the group Hk. Define a map phi from H to Hk mod K, where phi of X equals Xk. The well-definedness and the criteria of being a homomorphism can be trivially checked, and it's clearly surjective due to the fact that each coset Xk in Hk mod K has a corresponding pre-image X in H. Then the kernel of this homomorphism is exactly H intersects K. Since the kernel of phi is a set with all elements X in H such that phi of X equals K, then X must be also in K. Therefore, kernel of phi equals H intersects K. Thus we have a canonical isomorphism H mod H intersects K to Hk mod K. Since we know that there exists a canonical map psi from H to H mod H intersects K, where psi of X equals X H intersects K, which kernel of psi equals H intersects K, we can construct a map F from H mod H intersects K to Hk mod K, where f of X H intersects K equals Xk. Then F is a homomorphism can be trivially verified. For injectivity, let Yk equals Y prime K, which implies that Y inverse Y prime is in K. Since Y and Y prime are in H, so as Y inverse Y prime in H. This means that Y inverse Y prime is in H intersect K, and hence Y H intersects K equals Y prime H intersects K. In terms of surjectivity, it's true because for each Xk in Hk mod K there is a corresponding X in H, the pre-image X H intersects K in H mod H intersects K. Therefore, F is a canonical isomorphism, and H mod H intersects K is isomorphic to Hk mod K is called the second isomorphism theorem. So far I've shown the second isomorphism theorem. Thanks for watching. If you'd like to follow my math journey, consider subscribing to the channel. That's it for this time. I'll see you in the next video.